Okay, everybody, so we have the second talk today. This is Ben Tapley, originally from Australia, now a student, PhD student in Norwegian University of Science and Technology. Talked about us about some new results in particle tracking in discrete, incompressible flows. Please, Ben.
Thank you, Bruno. So I'm going to be talking a little bit about simulating systems of particles in incompressible fluids. So this is a joint work with Helge, Eleanor, and Brynjulf. So Helge is from the numerical turbulence department at NTNU. So basically, the application of this project is in simulating ice cloud dynamics, spread of pollutants in the atmosphere from combustion processes, for example, spread of microplastics in the ocean or rivers, migration of plankton in the ocean, pharmaceutical processes, and it has lots of other applications such as, say, nanoparticles moving in your bloodstream, or even making paper, for example. So basically, obviously, we won't simulate. So if you have an ice cloud, you have billions and billions of particles. That's very expensive to simulate. So we would like cheaper methods to do this, and if we can understand how the microscopic behaviors of these particles move, then that's a step forward to understanding the collective behavior of this. So hopefully I guess this can eventually lead to improving weather simulations, and hopefully on your weather app, you could actually predict some more accurate predictions about the weather. So basically, this problem can be broken down into a number of steps. I've put here in brackets 0 because we're really going to start off with, say, we're given data from a direct numerical simulation of Navier-Stokes. So there are hundreds of thousands of people working on these kind of, spectral element solvers, finite element solvers for simulating Navier-Stokes. So really we're going to pick up from number 1, so looking at the particle model. So this means basically you've got a particle, how do you determine the forces and torques on this particle? Okay, so obviously if you have an arbitrary shaped particle, that's very hard to do, so we have to make some assumptions. We're not actually going to talk about this so much today, but mainly look at the numerical methods here. But this is still related to the project, so we're going to primarily look at the interpolation of this discrete velocity field onto the location of the particle. And then we're going to quickly look at some integration methods for the resulting set of ODEs. So previously, the engineers use these methods, so polynomials which are not divergence free. So basically we're simulating or trying to approximate a vector field that's from the Navier-Stokes equation using, say, a tricubic polynomial interpolation. And that obviously destroys this structure, namely that it's a divergence free field. And also we use like a standard Adams-Bashforth method. These are used for a number of reasons which I'll talk about later on. So I guess I'm from a geometric integration background, so whenever we see some sort of structure, we like to see what it's like to preserve it. So we're going to have a look at what does enforcing this divergence-free condition for this interpolated vector field what benefit does it have on the simulation. In addition, we have some extra information that the data is from the Navier-Stokes solution, or a solution of the Navier-Stokes equation. So can we design a more specialized interpolation method with this information? So I guess polynomial interpolation is just a very, stock standard method. You can apply it to any vector field, but we've got some extra information, so can we exploit that to our advantage? And lastly, can the resulting set of ODEs benefit from a more geometric treatment? Okay, so we've got 3 sections to my presentation. We'll start off with some interpolation methods. So basically this is just a standard interpolation problem we're going to look at first. So if we have a set of data points, so a bunch of UIs, which are the fluid vector field, or the fluid vectors at the location X. Like I said, many authors use tripolynomial interpolation due to its simplicity. There are a few other more sophisticated methods, such as partial Hermite, Lagrangian polynomials, Fourier summation, and Taylor series methods. And these all have their pros and cons. For example, with this Hermite interpolation, we need the derivatives of the fluid field at these grid nodes, and that's a problem in itself. So how do you approximate these derivatives? And that, I guess, incurs extra computational costs. So with that in mind, and the fact that many people use polynomial interpolation, we're going to have this as a benchmark method. And again, a lot of authors argue that the errors from the interpolated vector field are averaged out when you consider thousands and thousands of particles, and they don't really consider it to be much of a problem. But this argument isn't so strongly supported with a lot of numerical, with I guess many studies and numerical evidence. So we're going to review a few interpolation methods. So try polynomial interpolation, and then we're going to have a look at scalar radial basis functions. That'll lead into what's called matrix radial basis functions, and then these are in fact divergence free. And then we're going to have a look at interpolation using regularized Stokes laws. So this is, I guess, taking advantage of this fact that our data is coming from the Navier-Stokes equations. So first of all, this is our benchmark method, tripolynomial interpolation. So this is what it looks like. Basically, we have these monomial basis elements, and our interpolating surface is called P. And the interpolation problem is to determine these coefficients here, the C's. And this is a linear problem, so all we need to do is invert a matrix A, and we can solve for this vector of coefficients. So interpolation of order S requires, S plus 1 points cubed, because we're in R3. So we have to invert a matrix of this size squared. Yep, so that's going to be our benchmark method, which will kind of compare the rest of our interpolation methods to. The next one is radial basis functions. So this is a slightly more sophisticated method, which hasn't really been used much in particle simulations. It's got a wide and far-reaching use in things like electromagnetics, because they can, again, define divergence-free vector fields, as well as neural networks and machine learning algorithms. So instead of our monomial basis, we're now going to use these radial, these scalar radial functions as our basis for our interpolation vector field. So what we do is, for example, this could be a Gaussian. All right, so we've got a set of data points up here. We just plonk a bunch of Gaussians located at these data points. Okay? And the interpolation problem, like before, is to find these coefficients such that the resulting vector or the resulting surface is consistent with the data. So again, that's a linear problem, and this often results in a much better approximation to the vector field or to the data than polynomials. This isn't quite divergence free yet, because we can only really do this point-wise or component-wise. So if we have a vector field, we just do this once for each component. So we can make this vector field divergence free if we use matrix radial basis functions. So here are just some examples of radial basis functions. So again, we've got Gaussians, these multi-quadrics, and so on. And I might just quickly mention, we're talking about matrix radial basis functions, that these depend on the shape parameter epsilon, which determines the flatness of our surface, of our Gaussian, for example. And generally, the flatter these radial basis functions, the better our approximation is, but then we get a more ill-conditioned linear system. So we have this side condition, and we can use matrix radial basis functions to enforce this side condition. So this is what a matrix radial basis function looks like. We have an RBF here, a scalar radial basis function. Then we have this matrix differential operator, which we apply to this scalar RBF. and that defines this vector field. So now our vector field is a linear combination of these matrix radial basis functions multiplied by just a coefficient vector. And now the interpolation problem is to solve for these coefficients. So we can prove that these are divergence free. So we just take the divergence of just one of these phi times ci's. Okay, we have this. Then using this double curl identity in R3, we can transform this operator into the double curl, and then again the divergence of the curl is 0. So that means this combination of vector fields is divergence free, which is good.
Sorry, is that like representing your thing as the curl of somebody?
Yeah, so it's...
But it's still built out of a scalar function, psi, everything is depending on the scalar function.
Yeah, but we have this matrix operator acting on it. So this is kind of like, it's almost like a stream function. But I guess it's the curl of a curl, so... So here are some results about matrix valued radial basis functions. So if this function is positive definite, then the interpolation matrix will also be positive definite, and therefore it will be invertible and it's well posed and we have a unique solution and everything works well. So this is kind of the remarkable thing about radial basis functions, is that if we just choose any old function for psi, we'll not likely end up with a well-conditioned system, a well-posed system. For instance, if these are just monomials again, we need exactly s+1 points in each direction, otherwise the problem's not very well posed. Again, the data can be scattered, so we don't require a regular grid to do our interpolation on. So this is very good when we're looking at Navier-Stokes solvers on non-regular grids, and in this scenario, polynomial interpolation becomes very cumbersome. And again, we have C-infinity surfaces with slightly higher regularity between cells and infinitely many non-vanishing derivatives. And this is good because when in some particle models we need the derivatives of the fluid fields to specify the torques. And if you take a derivative of a polynomial, the order goes down by 1, and then it's a slightly worse approximation to the derivative of the true solution. So it's been shown that radial basis functions actually approximate the derivatives slightly better as well. So that's another bonus. Okay, so now we've got a matrix radial basis function interpolation method, which can enforce this divergence free condition. But can we go one better and use some information about the fact that our vector field is coming from the Navier-Stokes equations? So really, there should be an underlying continuous field which kind of somewhat satisfies this to a very high degree of accuracy, because we use some sort of spectral element solver for this. So we are working with two assumptions. First one is that we are interpolating steady state solutions to 1, so we could ignore this time derivative. The second one is that when we're working with a direct numerical simulation to the Navier-Stokes equations, where for our step size x that does all these derivatives, they are very small compared to the smallest length scales of the fluid, namely the Kolmogorov scales. So at this length scale, we can ignore the nonlinear effects. In other words, the Reynolds number is very low, and we'll approximate solutions to this equation by the Stokes equation, which is given by these equations here. Okay, so I guess that's a fair assumption. At very small length scales, the fluid can be approximated by a creeping Stokes flow. This is done all the time. So now we're going to look at using exact solutions to this equation to do interpolation on Navier-Stokes data. So this is the question we're going to address now. One way to solve the Stokes equation is the method of Green's function. So if our forcing term is just a point force at the origin, then this is the solution to the Stokes equation. So now, this kind of begs the question, can we treat this like a radial basis function and create a vector valued interpolating surface from scaled and shifted Stokeslets? The answer to this is kind of, but not really, because there is a singularity here. So, I mean, if we scale this to the data points, we'll get a blow up at the data points. We can technically shift our kind of our knots, or we can evaluate these outside the interpolating domain and take the solution inside the grid cell, but that's very cumbersome and not much theory has been done on this, so it's probably not a good idea to go down that path. Instead, what we can do is regularize the Stokelet. So instead of having this point force here, we have a blob instead. So instead of a sharp Dirac or a sharp delta function, we have a smooth kind of bump which approximates the delta function, and it actually equals the delta function when this limit epsilon goes to 0. So again, you can think of this as a Gaussian, and then we also have to have it satisfy it's got a unit integral. So now we have, instead of a point force, that the force is kind of spread out over a small bowl and it decays to 0 far away from the center of this bowl. Okay, so now we're getting a bit technical. So if we define this G epsilon and B epsilon to be approximations to the Green's function. So now this is a regularized Green's function. And B is an approximation to the biharmonic equation, but so we can think of this B epsilon as a regularized biharmonic function. So we can take the Stokes equation here, just rewritten it, not done anything yet. We can take the divergence of the Stokes equation. Again, this goes to 0. Then we are left with just this equation for P, which we can solve. And it has a particular solution like this. We can re-substitute this back into the Stokes equation, and then we have a differential equation for U, which we can solve, and that gives us what's called the regularized Stokes-lit velocity. And up until now, we've just followed the theory in this paper by Cortez on basically where he just derives this equation. And this is where the paper leaves off. So basically, we do have an analytic solution to the Stokes equation when, instead of a point force, we have this blob force at the origin. That's what it looks like. So now we can ask again, can we do interpolation using scaled and shifted versions of this regularized Stokelet? And I guess we can, but the question now is it well posed, and is there a unique, does there exist a solution, and is it unique? So we can ask this question of well-posedness. Okay, so that's again equivalent to requiring that there is an invertible interpolation matrix. Okay, so how do we answer this question? Well, we can actually do that by the following. So we have a regularized Stokes here. I've just rewritten it again. We can use this vector identity, okay, which is not so obvious when you look at it, but it's quite simple to show. Basically, if you just write I was planning on copying it, but I guess it's f dot grad b. If you just want to take the ith component of this, that's equal to this f j. So we're summing over the j's times iv. And then this is a constant vector, so we can just into here. Then we have j, I, f, j, b. And then this is exactly equal to what we had on the right-hand side, which we were trying to show. And I guess it's just the ith component of that. So let's hope that matches this. Looks like it does. So that's good. So it's a very simple vector identity. We can just substitute that into here. And then use basically just the definition for G, put that back in. And then we can rewrite the regularized Stokelet like this. And does this look familiar to anyone? Yes. Yeah. That's exactly the matrix radial basis function element. If we identify this biharmonic function with the positive definite radial basis function psi. And also the force coefficients now are equal to the interpolation coefficients. So that's quite interesting. So we've got these radial basis functions which actually solve the Stokes equations. We don't even have to do anything extra. And that's extra good because now we can just lean on all the theory that has been proven with these radial basis functions. And these have been studied for 50 years, so we've actually just kind of piggybacked on that. So we know that now if we actually do interpolation via regularized Stokeslets, we're actually solving it's exactly the same as matrix radial basis function interpolation, which is fantastic. So here's, now I've just written this regularized Stokes solution in terms of these radial basis functions. So I've just substituted psi for B, and this is the resulting pressure term. Yeah, and then of course we can superpose these solutions due to linearity of the Stokes equation. Okay, so that's good. So now we've got even more reason to use these matrix radial basis functions because, well, first of all, they're divergence free, which was our initial motivation, but we also know now that we're solving these local Stokes problems. And that's also consistent with these particle models which we use for determining the forces and torques on these particles. We generally assume that they're small enough that we can approximate the flow with Stokes flow, and then we can use all these approximations from these creeping Stokes flow, and actually regularized Stokeslets are used a lot to approximate these fluid structure interactions as well. That's good, everything's kind of consistent so far. So now we're just going to look at this integration or an integration method for the resultant set of ODEs we have, and then we're going to look at some numerical experiments after. So I won't talk much about this. Mainly we have just these rigid body equations here, and then we have some forcing terms. So a force and a torque. Okay. So, and again, these come from the particular model that we use to model our particle. So we can write this compactly, and I guess as a geometric integration group, we like to write it as this kind of Hamiltonian system, or like this Poisson system. And then we have a forcing term here, which I guess is just a vector with zeros from the bottom up, and then we have an F and a T in the top, I guess the top 6 components. This is the energy of the particle, just to make it consistent. Okay, so I guess if you're familiar with splitting methods, it becomes quite obvious what we're going to do now. Oh, not yet. So basically, here we have this Stokes number, 1 over ST, which is the Stokes number, and that basically determines the magnitude of this force. Okay, so that's going to be important later when we consider the splitting method. So basically, as the Stokes number goes to 0, the particle behaves as if it was a fluid element and moves exactly along the streamlines of the fluid. But as the Stokes number goes to infinity, the particle behaves as a free rigid body, as if it was moving through a vacuum. Yeah, so we're going to split the vector field into this rigid body vector field and this vector field that's just governed by the fluid forces. And in this vector field, the position, this is the orientation, and time are constant. So this is quite easy to integrate exactly, and especially with the particle model that we're using, it's just a linear term plus a constant term, so we can use integration by parts. Variation of parameters formula there. Yeah, we're just going to use the strain splitting, where these two operators denote the exact equations, the exact rigid body solutions, and the variation of parameters formula. Yep. So again, we're going to compare this to what's typically used in the industry, which is an Adams-Bashforth method. And one of the reasons why they use that is because you only evaluate the vector field at integer multiples of the time step. And in these numerical solutions to the Navier-Stokes equations, we only have this vector field at integer multiples of the time step. So if we want to use like a high order Runge-Kutta method, we have to have all these stage values where we evaluate the vector field, and then we have to interpolate the data in time as well as space, and that's an extra layer of complexity and computational costs, which we can just avoid if we only evaluate the vector field at integer multiples of the time step. And here, if we put this, if psi2 corresponds to this, we only evaluate the vector field at integer multiples of the time step as well. So this is consistent with all of our design requirements. Yep, so now we're looking at some examples. So this is our particle model. We're just using an ellipsoid. Okay, it can be flat like a pancake or a bowl or a thin rod. And the forces and torques are given by Brenner and Jeffrey, and these are exact expressions if we have this creep and Stokes flow assumption. We're going to be looking at a discrete Taylor-Green vortex field, which is a steady solution to the Navier-Stokes equations. So this is somewhat realistic. Okay, and now for some videos. Go over here to play. So what we're going to look at now is, so TP1 stands for tripolynomial 1, which means we're just doing a linear, well, basically these particles are evolving on a linearly interpolated vector field, and we're integrated using Aaron-Forth 2. So there are two colors here. You can only see red now. Red is the numerical solution, and black, which is underneath the red one now, is the reference solution. So that's taken to be exact. So this is what it looks like. This is the best part of the presentation, by the way. All downhill from here. Now there's more videos, so maybe I'll just pause it right at the end. So obviously, this doesn't look right. So we've got these particles which have just gone a bit nuts. Yes, yeah, so
that's probably mostly due to the non-smoothness, isn't it?
yeah, exactly. So we have these
really bad
discontinuities between the grid cells. So the particles sometimes hit the grid cell and something happens. And again, obviously the black curve, which is the reference solution, it's very smoothly distributed along this whole line. So these are dots, which are all evenly spaced because I guess that's what they're distorted just due to the fluid, but I guess these red dots are distorted due to numerical errors as well. And then we have these gaps along the solution here. So we lose some regularity in our solution as well.
Can you remind me how you computed the reference solution?
Yep, so just like a Runge cutoff 4 method, but because we have an analytic solution, we can evaluate the vector field everywhere. And
so you do have an exact solution that you compare it to?
Yeah, exactly. So this is the Taylor-Green vortex.
Oh,
yeah.
right.
So if we did it in
Yep.
an actual numerical data, then I don't know how we can do the reference solution. So everything here is just Taylor-Green vortices.
Okay.
Yeah, okay, so let's see if we can do better. Let's go to a quadratic interpolated vector field. So there you go, slightly better, but not perfect. So maybe we'll pause it at the end. So again, you can see it's much smoother along here. This is really the problematic part. And then, but we still get some discontinuities here where we have this erroneous clustering of the particles due to the low regularity between the grid cells. And you can see here it's nice and smooth, and there's a little gap here, and that kind of corresponds to I guess this is due to those cell interfaces.
How big are your grid cells?
0.1. And I guess the Taylor-Green vortices. This is 1, so you've got 10 points along here. Right? So I guess that's quite rough just to showcase the power of matrix radial basis functions. So now we're going to use tricubic vector field. So these are good because these are C1 in between grid cells. So they actually have a continuous first derivative everywhere. This should do a better job. So far, so good. Okay, so that's a lot better, right? So if you skip to the end, it almost agrees, well, it agrees pretty well with the reference solution. But then at this spot here, we get something which is happening. Not sure why, but just leave that for now. Okay, so let's have a look at how radial basis functions perform. So this is MRBF1. So again, I guess linear interpolation kind of uses this cube of data points. That's what I've called TP1. And then TP2 uses a slightly bigger. And then same again for TP3. And then this, I've also called this MRBF1 as well, and this is MRBF2 and so on. So basically, MRBF1 is the same computational cost as TP2 because we're inverting a linear system of the same size. So really, we should compare MRBF1 to the first one we saw with the linearly interpolated vector field. Let's see how this goes. So that's a lot better. As you can see, the solution is much smoother. We don't have these gaps in between along the line here. But we do have these distortions. I guess that's just due to error of the vector field and not really these irregularities between the cell interfaces. So that's looking a lot better already. Now let's go up to an extra data point in each dimension. So we'll look at MRBF2. Let's see how this goes. So that's the best one yet, right? You can barely distinguish the difference between the two lines. So right at the end, that's looking very accurate. And then I haven't shown MRBF3 because it looks pretty much the same. So this is the error which we're looking at. So as we can see, this MRBF1 plus, I guess we've also got the splitting algorithm here as well as, and the Adams-Bashforth algorithm for the polynomial interpolated vector fields. So this is this pink one here, that's MRBF1, and that's even better than quadratic polynomials. And again, MRBF2 is better than tri-polynomials, or tricubic polynomials. So here I've just measured the error as just the average error over, so the difference between the reference solution and the numerical solution is taken average over the 1,000 particles in the ring. But in application, we don't really care so much about the error per particle, right? So if we have an ice cloud and it's doing this, and we calculate that this ice particle this snowflake is slightly wrong here, that's not so important. We really care about what the distribution does. So if you measure these particles, if you measure, say, 10,000 particles, a better, I guess, a better measure of the method's performance is can it reproduce a good distribution of particles, okay? So, sorry, a bit out of order here. I just finished this presentation an hour ago. So here I might just say that we've measured the error versus the Stokes number, okay? So basically, if we have a really viscous fluid, that corresponds to a very small Stokes number. And if, say, we have a very inertial particle, for instance, like a lead bowl in air, then that corresponds to a large Stokes number. So this is really the magnitude of the fluid forces along the x-axis. Because we're using a splitting method, we actually pick up this order epsilon accuracy as we increase the Stokes number with our in our splitting method solutions. So the pink and blue are the splitting methods, and the Adams-Bashforth kind of is independent of the Stokes number. So we gain accuracy as the Stokes number increases. So that's good. Another thing to notice is that the pink solutions, they're the matrix radial basis functions. They're all better than the corresponding tri-polynomial solutions. One other thing to notice is that we have this region here where the splitting methods are all stable and the Adams-Bashforth solution blows up. So this is a bit misleading because it is a logarithmic plot, so we can actually go up to 10 times the Stokes number and still have stable solutions. However, we do get order reduction here, but I guess that's better than the solution going unstable. That's for another talk. So I promised that we're going to look at distributions of particles now. So I mentioned here, so we're not so concerned with just this error in the way that I presented it before as the average error between particles. And in fact, yeah, a lot of authors claim that this error is averaged out when we do simulations with tens of thousands of particles. So then we'd like to look at how a distribution of particles compares to the reference distribution. Okay. So two natural ways to compare these discrete distributions are the relative entropy and the first Wasserstein distance, aka the Earth movers distance in the, I guess, computer science community. So now, we're going to look at more videos. So in here, there are 10,000 particles in a small little box that are computed, and this is on the linearly interpolated vector field. Whoops. Let's try it again. This is how it looks. Oh, we've moved to TP2, sorry. Anyway, maybe I'll just start with this one. So with the quadratic polynomials, we notice that there's this big empty region here where we only have the reference solution and no red dots. So that's quite a large error. So these quadratic polynomials don't actually capture this feature of the solution. I'm not really sure why, but there must be something going on here. Maybe it correlates to like some stagnation region which these symmetric polynomials don't quite capture. Let's go back to the linearly interpolated vector field. Something similar. We get a lot of clustering here, which is missed by the red dots. Then we get some particles here, and I guess if you watch this evolve, maybe I'll stop at the right time. But see, we have this erroneous velocity here, so the red dots don't really keep up to the black dots here. So we do get a lot of mismatch, and it's quite easy to see at a visual level. Tricubic polynomials, so this is the best polynomial solution we had. That's, I mean, looking more or less good. It's really hard to say now because, I mean, now we're going to have to look at these more sophisticated error estimates, the error measures of these distributions. And this is the MRBF1 solution. So this is the most, this is the cheapest matrix rated basis function solution. And that looks quite similar to the tricubic one, which is the most expensive polynomial solution. Okay, so we go to the end. Again, who's to say which one's best, this one or this one? Well, what we can do here is we can compute the Wasserstein distance and the relative entropy. So here's the error, the relative error in the same way I presented it before. So this is the average error over all the particles relative to the reference solution. And what I've done is I've divided all these numbers by the tricubic one. So this is just equal to 1 here. So this is relative to the tricubic solution. So the main thing to note here is that, okay, so the MRBF2 solution, it has worse relative error when you measure all the particles, you know, relative to the reference. But the Wasserstein distance of this distribution is actually better than the tricubic solution. That's quite interesting. And same goes for this relative entropy. It's actually a lot lower. So what is this saying? Relative entropy first Wasserstein distance is lower despite having a higher average error per particle. This is quite good. This is interesting because now it's really actually showing that these errors are actually averaged out in a much better way than with just using a simple polynomial vector field. So that's, I guess, the main observation there. And I guess we could also say that this MRBF1 solution is doing a lot better than the polynomial solutions. In this is a particularly bad example for the quadratic solution because we have this very bad, a lot of particles which do the wrong thing, so that gives us a very bad error here. This is the Stokes number of 5. I did the same thing for a different Stokes number just to check it wasn't a fluke, and we get similar results. So here we have, again, that the MRBF2 solution has worse error, but it represents a more accurate distribution. So that's quite good. So this means that, okay, then perhaps these errors are kind of moving in the correct way. It makes it look like a more qualitatively correct solution. So to conclude, we've shown that matrix rated basis functions are equivalent to solving the local Stokes problem on the grid. So this could somewhat explain why we get qualitatively better solutions. We use the splitting method, which was better than an Adams-Bashforth method. We see some erroneous results from polynomial interpolated vector fields. We get better averaging out of errors with MRBFs. And I guess we'll extend these results to other models such as slender bodies, which we've been collaborating with a PhD student from America with. So I guess that's just, we're going to look at other particle models, and of course we probably have to look at, I guess, numerical simulations of Navier-Stokes as well, and move away from these analytic Taylor-Green vortices. If you'd like to find out more, you can speak to me or look at our preprints, which was up on archive at 2 AM this morning. Hot off the press. And here are some references that I used.
Question, Robert?
So the results you showed, that was for the Stokes slit one, is that right?
Yes.
Is there any difference between the different RBFs?
Not really. So all the RBFs correspond to a different Stokes slit.
Yeah.
And I tested them on, they're more or less the same. So
What order are they in space? These RBFs?
They have spectral convergence.
Spectral. Okay.
There's no order.
And my other question was, have you thought about doing volume preserving integration since the flow is incompressible?
The flow is incompressible, but the ODEs aren't volume preserving because they're inertial, right? So they don't follow the streamlines of the vector field. But we did do a little project with just computing streamlines of massless particles, so trace particles, and looked at volume preserving. We used the volume preserving algorithm of Feng and Kang, I think it was, and because the MRBFs are volume preserving, so the vector field is actually exactly volume preserving, and we did this, and we get much better results as well. Yeah, but I don't think we can apply volume preserving algorithm to this set of ODEs.
The fluid flow isn't coupled to the particles at all. The particles are just being carried along by the flow.
Yeah, so it's what we call one-way coupling,
Yes,
right? So the particles kind of are affected by the fluid, but the fluid evolves independently of the particles as if they weren't there. Yep.
Because I know people in the Met Office who kind of do this a bit for a living.
Okay.
That, it's very important to the dispersal of pollutants. So, or volcanic ash, or other things coming from power stations that blow up. Was the famous first example. Big fires, where's the smoke going? So I was just thinking, that there are people doing it, and maybe what you're doing is of interest to them. I can give you a name in the UK Met Office.
Yeah, okay, that could be interesting. Yeah, there may be that.
There is a little if that is, this is direct numerical simulation, and I don't believe you can do weather prediction with
Yeah, that's right. So she's got not weather prediction. She's taking a prediction in order to predict where the pollutant is going to go. So that's why I'm asking.
Oh, using
that
like
there's
initial conditions.
So if you were given the prediction of the winds, then you could presumably do something. Yes, if you.
Yeah, definitely. Yeah, I think there was a paper that I read that looked at some like a RAND simulation of turbulence and just had a look at how accurate that compared to the direct numerical simulation. And so I think there are people that kind of try and bridge the gap between direct numerical simulation and more large scale.
Well, I mean, she's given a prediction from another department.
Okay, so
she's not producing them.
Yeah.
The big thing is where do the pollutants go? And presumably the pollutants have different properties. Like some of them are flakes. And they have different weights and blah blah blah. So
like Stokes numbers and different models.
I
and,
mean, I'm just thinking that there's a lot of. I'd say you'd have a big audience.
Okay. Well, think about that.
So can you now conclude that the assumption that the error is averaged out, the interpolation error is averaged out, that this is a wrong?
I guess maybe it's still somewhat correct, but it's more strongly supported with MRBFs, I would say.
Right.
Yeah.
What about solving this big linear system to get the RBF? Are there fast algorithms for that?
Yeah, so actually on a regular grid, this linear system is like block Tapley. And then you can, there's actually an algorithm that you can invert that exactly, and then you can do that. But I think if you're just on like this, the linear system is 27 by 27, so it's not huge.
Right, because WX is really big.
Oh no, because you're only doing it in one grid cell, right? So it's just you. I guess I mean
I thought the IBF was global.
it is. Yeah, you could do the whole domain, but I think in the algorithms of the engineers, they kind of just they have like a particle or they just have a. I don't actually know. I think they just use like these splines. And they just kind of solve it kind of piecewise, and they don't really have this whole domain. I think that's somewhat because if you do that, it's just too much memory requirements, and so you really need to do it just locally, and then you throw away the information. But is that correct? I'm not so connected with the engineering side.
I don't remember any longer, but I remember
Yeah.
it's important to localize.
Because I mean, when you have these spectral element solvers, you have all these these polynomials within the cell, and then they're defined globally. So why can't you just keep them and not even worry about an interpolation algorithm? But the reason you don't do that is because that takes up way too much memory, and the computers can't really handle that.
It's getting a little bit late, but Ben is going to be here for the next few weeks, so it should be a lot of opportunity. The door is always open, right? So you can discuss this more of the next month. So let's thank Ben